Imagine shining a light onto a wall with two tiny slits. Behind the wall is another wall, ready to capture the light that passes through. You might expect to see two bright lines where the light shines through the slits. This is classical physics at play. But the quantum world dances to a different tune. In the quantum realm, something extraordinary happens. When we fire individual particles of light, photons, at the two slits, something strange occurs. Instead of two bands, a pattern of multiple light and dark bands appears. This pattern, known as an interference pattern, suggests that the photons are behaving like waves. These waves interfere with each other, creating areas of high and low intensity. The double-slit experiment, simple in its design, shook the foundations of classical physics. It revealed the wave-particle duality of light. Light, it seemed, could act as both a wave and a particle. How could something be two things at once? This question puzzled physicists and paved the way for the development of quantum mechanics. The idea that light could be both a wave and a particle was a radical one. For centuries, scientists had debated the nature of light. Isaac Newton, a giant of classical physics, believed light was made of tiny particles. He called them corpuscles. Later experiments, however, showed that light exhibited wave-like properties like diffraction and interference. The double-slit experiment brought this duality into sharp focus. When light passes through the two slits, it interferes with itself like a wave. This interference creates the distinctive pattern on the back wall. But when we try to observe which slit the photon goes through, the interference pattern disappears. If we try to pinpoint the photon's path, it acts like a particle again, passing through only one slit. This duality is one of the most bizarre and counterintuitive aspects of quantum mechanics. It suggests that the very act of observation influences the behavior of light. Surprisingly, the wave-particle duality isn't limited to light. Even particles with mass, like electrons, exhibit this strange behavior. In the 1920s, physicists demonstrated that electrons fired at a double slit also produce an interference pattern. This discovery was astounding. It implied that matter, like light, could also behave as a wave. The implications were profound. If matter has wave-like properties, it means that our everyday understanding of particles as tiny, solid objects is incomplete. In the quantum world, particles exist in a superposition of states. They are not simply waves or particles, but possess the potential for both. The act of observation collapses this wave function, forcing the particle to choose a definite state. The observer effect. Does consciousness shape reality? The role of the observer in quantum mechanics is a source of much debate and philosophical pondering. Does our consciousness, the act of observing, actually influence the outcome of quantum events? The double-slit experiment seems to suggest so. When we don't observe which slit the photon or electron goes through, it exists in a superposition, going through both slits simultaneously. But the moment we try to observe its path, the wave function collapses, and the particle chooses a single path. This has led some to interpret quantum mechanics as implying that consciousness plays a fundamental role in shaping reality. However, most physicists offer a less mystical interpretation. They argue that observation doesn't require a conscious observer. Any interaction with the environment, like a detector measuring the particle's position, can cause the wave function to collapse. Einstein's reservations, a genius grapples with uncertainty. Albert Einstein, despite his groundbreaking contributions to physics, famously harbored reservations about quantum mechanics. The probabilistic nature of quantum theory, where outcomes are based on chance rather than definite laws, deeply troubled him. God does not play dice with the universe, he famously quipped. Einstein believed that quantum mechanics, while undoubtedly successful in its predictions, was incomplete. He spent years searching for a deeper theory, a hidden reality beneath the probabilistic haze. He engaged in famous debates with Niels Bohr, one of the pioneers of quantum mechanics, challenging the very foundations of this new physics. While Einstein's quest for a deterministic theory ultimately proved unsuccessful, his skepticism and relentless questioning pushed the boundaries of quantum mechanics. His insights, even in disagreement, helped refine and deepen our understanding of this strange and wonderful realm. Quantum wonders. embracing the enigma. The double-slit experiment, with its demonstration of wave-particle duality and the observer effect, offers a glimpse into the baffling yet magnificent world of quantum mechanics. It reveals a universe where particles dance to the rhythm of probability, where the very act of observation can alter the course of events. While some aspects of quantum mechanics remain mysterious, its impact on our understanding of the universe is undeniable. It underpins our modern technology, from lasers and transistors to medical imaging and nuclear energy. More importantly, it challenges us to expand our perception of reality. The quantum world invites us to embrace uncertainty, to marvel at the counterintuitive nature of reality. It reminds us that the universe is far stranger, far more wondrous than we could have ever imagined. And as we delve deeper into the quantum realm, we can be sure to uncover even more awe-inspiring secrets that challenge our understanding of the cosmos and our place within it.